Yo, what's up, gamers? It's midnight on a Sunday. I just got off of work, and we're gonna talk about some fucking numbers today, boys. Let's get to it. Specifically, we're gonna talk about these guys called transcendental numbers. What are they? They're kind of spooky. That's why they're so interesting. I've been obsessed with these things for like the last 2 days. They're spooky because they're like my first impression of transcendental numbers were like these shouldn't exist, but they do. They're really really strange to think about. The fact that they can exist in the first place, it almost seems paradoxical. And we're going to get into why that is and why these things are so spooky and go over some examples and stuff like that. Alright, first of all, sorry for the fantastic lighting quality in my room. Just now realizing that's a thing. We're just going to roll with it. Like I said, it's midnight. I don't got a better option. Anyway, to understand transcendental numbers, we have to first talk about their kind of twin category called the algebraic numbers. What are algebraic numbers? You could probably guess from, the name algebraic numbers. Gee, I wonder what that means. An algebraic number is any number which can be a solution to a polynomial, right? So we can generate like all the whole numbers, all rational numbers, real numbers, complex numbers, just by writing down some polynomial, right? And the key here, I guess, this is a little bit of a technicality, not too important, I guess, but it has to be a finite polynomial, not too important. Anyway, algebraic numbers, they're like the numbers that you use every day, more or less. What else can I say about these? I'm winging this one too, by the way. That's kind of all you need to understand. So, on the other hand, the opposite of algebraic numbers are the transcendental numbers, these bad boys. And the reason why they're so spooky, in my opinion, is the idea behind why these numbers exist. It's the idea that there is no possible polynomial, no possible finite polynomial equation that you can come up with which will have one of these numbers as a solution, which is like really, really freaking crazy to think about. It's like, how do you go about proving that? How do you, it's like, you can come up with some pretty wacky polynomials, right? That's like the whole point of math, really, is for a lot of, different theorems and areas of math is just coming up with really, really crazy stuff. And the fact that there exists numbers, not just any numbers, some of these are like really, really important numbers that cannot possibly be a solution to any possible polynomial equation, is like it's like discovering black holes. It feels wrong, kinda, at least to me. It just feels wrong. It feels like it's a paradox, which is why I'm so fascinated by these stupid things. To be clear, these are not all of them. There's another really, really spooky fact about transcendental numbers, believe it or not. There are more transcendental numbers than algebraic numbers. Let that sink in, bro. There are a whole order of magnitude more transcendental numbers than algebraic numbers. To be specific here, the set of algebraic numbers is what we call countably infinite, whereas the transcendental numbers are uncountably infinite. It is weird. It's just weird. Yeah. I don't know where else to put this fact also, but it should be important to note, maybe for the study of these things, is that transcendental numbers are also always irrational numbers. Not all rational numbers are transcendental, keep that in mind, but all transcendental numbers are also irrational. So as I said, one of the important problems, or maybe not problems, but like important ideas of transcendental numbers is thinking about like, where do these numbers come from? Like, what tools do we have to detect these numbers? Are they just random, or do they have some pattern? And it turns out it's a little bit of both. We haven't fully solved these yet, but we do have some idea of where transcendental numbers come from. And there's a few theorems, theorems to describe this. So the first one should state that when we say A or B, we specifically mean algebraic numbers, right? So A and B are both algebraic. So number one, e to the a is transcendental. Number two, a to the power of b is transcendental, but only if b is also irrational. And finally, the natural log of a is also transcendental. So there's a whole bunch more than that. I think these are the important ones. The names of these theorems also aren't very important. Don't worry about it. And these are very important for solving certain, figuring out if certain numbers are transcendental, because one of the main points of transcendental number theory, studying transcendental numbers, is there's a lot of different constants, very important ones at that we aren't sure if they're transcendental or not, and knowing whether or not these numbers are transcendental are very important. For example, like the Euler-Mascheroni, I think that's how you say it, the Euler constant, coming soon video. So it's an incomplete sort of field, right? There's one very important conjecture that hasn't been proven yet, which states that e to the c is transcendental if c is a complex number, right? Which this would basically generalize a lot of different results in transcendental number theory, or answer a lot of different questions, right? Some other like constants that we want to know if they're transcendental or not is like e plus pi, for example, or like pi to the power of pi, maybe. I don't know off the top of my head, right? There's a whole bunch of these. Like I said, there's like a whole order of infinity to the transcendental numbers, and we want to have a better idea of how these things occur, right? That's like the whole point of number theory. They're just really cool, man. I'm just telling you, man. They're just really freaking cool. So yeah, coming up, when I get the energy to do so, I actually want to go over the proof of why pi is transcendental. Showing that e is transcendental is pretty obvious. I mean, you just plug in 1 for this and you get that e is transcendental. That's not too interesting. But the proof for why pi is transcendental, right? Because pi doesn't match to any of these formulas, any of these theorems. So the reason why pi is transcendental is actually, it's a really, really cool proof. It's very, very simple. It maybe takes like a couple minutes to describe. But it's really, really clean, and it's really, really pretty. It's a really pretty proof. So I'll go over that some other time. Anyway, spooky math man. Bye.